My name is David Godwin, and I'm the coordinator for the Southern Fire Exchange with the University of Florida. Joining me today is our Southern Fire Exchange Program PI and former University of Florida professor, Dr. Alan Long. Today, we're excited to have our guest speakers, Jim Brenner with the Florida Forest Service and Dr. Matt Jolly with the U.S. Forest Service. Jim and Matt will be giving a presentation about their recent work to develop a new system and tool for estimating fine dead fuel moisture in southeastern vegetative fuels. Finally, if you're joining us today from an area outside of the southeastern U.S., and you haven't already, please look into connecting with your folks in your local Joint Fire Science Program Fire Science Exchange Network. These are the people that are working to connect regional land managers and researchers to address local fire science issues. So you can click to go to firescience.gov, and there's a map, and you can click to connect with your exchange in your neck of the woods. So finally, it's my pleasure, and without further ado, to hand things over to Alan, who will be introducing our speakers today.
Thank you, David. And it is my distinct pleasure to introduce both speakers today, both of whom are widely recognized for their roles in fire science and management. And as you will see in a moment, there are several special celebrations that align with today's webinar. Matt is a research ecologist in the Fire, Fuel, and Smoke Science program of the Forest Service Fire Sciences Laboratory in Missoula, Montana. He received a BA in Environmental Science from the University of Virginia and a PhD in Forestry from the University of Montana. He is the project administrator for the research and development team of the Wildland Fire Assessment System and is continually evaluating and developing tools for landscape scale fire danger assessment. He has been a member of more than 24 S491 intermediate fire danger rating cadres nationwide, and he has been a member of the Advanced National Fire Danger System cadre since 2006. His research explores how wildland fuel characteristics vary across space and time, and how these variations impact wildland fire potential. Ultimately, his work will lead to improved wildland fire danger and fire behavior prediction tools. We will hear about one of those tools today. And today is Matt's birthday. Our other presenter is Jim Brenner, Fire Management Administrator with the Florida Forest Service. Jim graduated from Penn State in 1974 with a BS in Forest Science and from the University of Warsaw with an MS in Forest Utilization and Pathology in 1979. After completing his studies, Jim went to work for the Florida Forest Service, then the Division of Forestry, as a forest ranger in the Flagler County area in 1981. In 1982, he was promoted to the position of Palm Beach County Forester. In 1984, again promoted to the position of planner for the division, and in 1985 to his current position of programs administrator in charge of fuels management, fire behavior, and fire laws. One of his most outstanding accomplishments has been the development of the Prescribed Fire Act of 1990 that protects the rights of responsible burners in Florida. The purpose of the law is to promote prescribed fire in Florida as well as train those using this important management tool. In addition to this, Jim developed and implemented the Interagency Basic Prescribed Fire Training Program in 1989 for certified burners, the Fire in Florida's Ecosystems Program in 1996, and the Florida Certified Pile Burning Program in 2006. Jim has also served nationally in more than 50 major wildfire incidents as fire behavior analyst, with the job of projecting fire growth both in size and direction. In 2016, the International Association of Wildland Fire awarded Jim the first Excellence in Wildland Fire Management Award at the 5th Fuels and Fire Behavior Conference in Portland. Jim's career has been instrumental, perhaps I should really say pivotal, for prescribed burning programs in Florida and across the South. But perhaps most significant today, he will be in full retirement mode in about 3 hours. Congratulations, Jim.
All right. Well, welcome, Matt and Jim. We're excited to have you with us today. And just one moment as we pull up your presentation.
Okay, I guess I'm going to start out here. I'm going to take very little time in this beginning just to go over why we thought this whole idea of developing a fine fuel moisture, dead fine fuel moisture model was necessary. And I've been actually preaching this for about 25 years, and finally was able to come up with the funding. And one of the first persons I thought of to do this was a person I worked with at the Advanced Fire Danger Rating class in 2006 at NAFRI. Matt and I were together in one group, and he impressed me as being a really smart guy and very capable. And I was particularly impressed when he talked a little bit about his background, and he said that he originally, or previous to coming with the U.S. Forest Service, he had been with the military, and one of his most interesting experiences with them was when one of his commanders told him that he was not paid to think, which I think is probably a big mistake on their part, because that's probably why he's not with them anymore. At any rate, what we found with respect to fine fuel moisture in the southeast, and we'll get to this in one of the points, is that the highest you can get from the current tables in Rothenmel's predicting for range management, predicting the spread of wildfire, is about 24%. The moisture of extinction for fuel model 7 in the older FPPS models is about 40%. So obviously this thing was not made for us. And so we needed something that was more relevant to what we were doing. So today's commonly used fuel moisture guide, they were created a long time ago when we didn't have a lot of the information that we have today. They're not based on equations and are only available in table form, and this makes applications extremely difficult. The guides often poorly predict the actual fine dead fuel moisture, and everybody who knows anything about wildland fire knows that's what moves a fire. And as this is particularly true in the humid southeastern states. And they don't account for seasonal variations in moisture content, and they do not account for rainfall in any form. So this next point is the one I was talking about earlier, is fire spread models used in the southeast have a moisture extinction of 40%, and current field reference tables never get anywhere close to that. So the old moisture tables don't go above about 20% moisture content. Making the calculations as simple as possible, and also make them mobile enabled for quick calculations. So this is an example of the current tables that we have available. We have the reference fuel moisture that we were able to come up with, and that's in this table. And then we do we use the second table to be more specific as to how to either increase or decrease, or usually increase the reference fuel moisture. So bottom line on it is that's how we do it now. And from this point, I just want to say one last word, is that this was not just a Florida effort. We had help from 7 other of the 13 southeastern states sending samples to Matt to make this happen. And their contribution was extremely important, and we want to recognize them as well. So from this point on, I'll let Matt take over.
Thanks, Jim. So one of the major problems that we face trying to calculate fine dead fuel moisture in the field is that the fine dead fuel moisture calculations that we're forced to use do not include important weather variables that we know drive variations in fuel moisture. One of them is rainfall. One of them is directly incorporating things like insulation, so solar radiation. But I can't stress the importance that the only form that the current calculations exist in is in a table form. So applications that have to use these fuel moistures literally have to go and look up values out of tables and add values together. There are no set of governing equations that can be used in other applications that can basically reproduce the tables in their current form. So our challenge was actually to try to take a new approach and a much more modern physically based model and try to simplify it to the point where we can develop a simple set of equations that can then be used to derive a table that can be used in field. And it's really useful because tools like Behave Plus already have this calculator built in, but it literally is built in table form. So you can't just put in the measured air temperature. You have to put it in for ranges of temperature, ranges of humidity. You get these reference values. You add these very rudimentary corrections that nobody, either a lot of them don't get used at all, or people basically just dismiss. But a good system would allow us to plug an actual equation in to our operational systems, so Behave Plus and the other ones we'll talk about later, the spatial systems, but also allow us to use it in the field by deriving a set of tables that are meaningful and actually be something that we can trace back to an actual physical description of how fuel moistures work. So one of the things that's really made this possible is the development of the Nelson Fine Dead Fuel Moisture Model. This model was developed and published in 2000, but it's really been picked up as the basis for a lot of the systems that we use operationally nationwide. So for both fire behavior and fire danger, the model itself has some reasonably simple inputs, but some very valuable inputs. So it has things like, well, it works off of hourly data, which is very similar to the way we'd apply it by weather, sling weather in the field. But it also has a couple of other inputs. So we know that temperature and humidity are very important for fuel moisture, but we also know that the two things that aren't in the current way that we calculate fine dead fuel moisture in the field probably drive a lot more of the variation. And one is the solar radiation, which we generally get around by expressing things as shaded or unshaded or sheltered, unsheltered, and then a direct input of precipitation. So the model has these 4 hourly inputs, and if we can figure out a way to abstract the logic of a very complicated model and put it into a form that we could actually use to estimate fine dead fuel moisture in the field, then we can leverage that for future to create this set of tables. So the model itself is a fully physically based model. So it's a set of partial differential equations and that deal with the diffusive and capillary water transport inside the fuel. So you establish the boundary layer atmospheric conditions, and it determines whether or not moisture is moving in and out of the fuel and at what rate. So consequently, it's actually quite complicated to calculate, and it's not practical to do it by hand in the field. So, but it has some really nice benefits. One of them is that it derives a surface temperature from an actual energy balance, looking at the net heat of gains and losses, or the net input of gains and losses, and we'll look at that in a minute. But that allows us to incorporate things like the effect of solar heating on fuel temperature, the effect of solar heating on the near surface vapor pressure, and how that changes the way that moisture moves in and out of the fuel. The model that we use is scalable to any size class. So basically you can define the size of fuel that you're interested in. So we stuck with the description of a 10-hour fuel because we knew we wanted to be able to carry over information about how the fuel moisture is changing over time. One of the problems with our existing tools now is that we calculate them as a snapshot in time, and we just assume that there's no lag in the fuel at all. And we know from working outside that doesn't work. That basically you have this sort of drying process that fuels go through once they get wet, or a wetting process that actually does take hours to accomplish it. So the moisture from the previous hour does have an effect on the current moisture, but the way that we calculate it now, it doesn't actually include any of that stuff. So, but being able to include things like solar radiation allows us to look at slope and aspect influences on fuel moisture directly, very much like how Farsight does with fuel moisture conditioning. Actually, Farsight already uses this model, so it's a nice way for us to be consistent with the way that we rate fine dead fuel moisture in all our applications. So the model is driven by this surface energy balance that's actually quite complicated, but it basically just equates to the heat losses, and the heat losses must equal the heat gains. So we have fuels that are losing heat through conduction, long-wave radiation, and evaporation, and they're gaining heat through solar heating and convective heating. Nelson actually derives this, but it turns out we can really simplify this logic since we're only concerned with one particular fuel type for our calculations. But it also incorporates rainfall directly, which is pretty great. So it means that we can actually wet a fuel, and then we can model the drying to see when those fuels become available later in the day, which is something that it's going to be a little shift for the way people think about things, but it's super important. The model itself has been extensively validated across in the Southeast and in the West, and so the great thing is that I'm pretty confident that if we can work out this any of the kinks for this system, it's going to actually apply nationwide, which means that we could actually replace the existing fine dead fuel moisture calculations that are in the IRPG or in the Appendix B for the Fireline Handbook, the Fire Behavior Appendix. All those things are quite useful. So, but what we want to do is we want to take this model, it's very complicated, and extract a simple set of equations that represent the logic as well as we can within our constraints, which are that we need to be able to calculate it from field measured weather observations or things that we can estimate by some proxy. And we just want to be able to have a paper calculator essentially in the beginning and eventually make it into a mobile app that's more dynamic. Just to put it into perspective, for a Nelson model typical calculation that divides the fuel into 11 nodes and does 80 calculations per time step, so basically it does 880 calculations, fuel moisture transport calculations in a given hour. So that's not going to work for what we need. So a simpler approach is going to buy us an awful lot. So just a few assumptions about what we're talking about. We basically stuck with this the definition of a 10-hour fuel, so we constrained Nelson to be the diameter of the midpoint of the 10-hour fuel class. And we know that there's some lag in the moisture calculations, meaning that the moisture from the previous observation is definitely going to influence the moisture from the current one. So we have to build that in a real simple way. And we generally expect that weather observations are going to be taken every hour in the field. So if we look at how, so the first thing we did was we wanted to use fuels from throughout the Southeast to actually calibrate a component of the Nelson model, and that's the equilibrium moisture content equation. So we had partners from 7 states, 25 sites around the Southeast, and they collected fuel, sent it to us in the lab, and we have this groovy conditioning chamber. So basically we can establish a fixed temperature and humidity and leave those fuels in there for a long enough time that they can reach equilibrium, and then we can measure their moisture content. And we can do that repeatedly for samples varying the temperature and the humidity across ranges. So this is it's a big table, and it doesn't really matter that much what it says, but it just gives you an idea of what we have. So we have needles and litter, and we have some grass samples and other types of litter from throughout the Southeast, from these 25 sites, 7 states, that we simulated the moisture content for 3 temperatures and 4 relative humidity combinations, so basically a matrix of 12. We develop a data set, and then we use that data set to calibrate the equilibrium moisture content equations, so or the saturation vapor pressure equation, sorry. And basically we get a very good agreement between the saturation vapor pressure, calibrated saturation vapor pressure, and our final or equilibrium moisture. So it's a good check that the base logic for the model actually works well for these fuels, and they're calibrated against Southeast fuels, but actually I don't feel like that's actually going to limit its utility to be applied anywhere else. So with the model development, I love this quote because it really summarizes my philosophy with all these things, is that everything should be made as simple as possible, but not simpler. This is not going to look like what you've done before, but it's going to give you capabilities that you've never had before. And I think that with some use and a little bit of probably slightly painful learning curve, once it starts getting used, you realize that it does have a lot of utility and is quite helpful, particularly addressing some of the problems in the Southeast. So the new fuel moisture model, what we have is basically an extraction of the logic in Nelson, meaning that we maintained all of the physical equations that are used to model moisture transport in Nelson, but instead of modeling the transport of moisture within the fuel, we just model the transport or the changes in moisture from time period to time period. So it means that we've basically taken Nelson's model and simplified it to run as a single calculation for a single time step with the same weather inputs. It's still based on the mass transfer logic that he used and then all the physics are consistent. The only thing we do is focus on how we derive this BI, which is the mass transfer BO number, and we did a sort of space for time swap in this equation 25, such that that instead of looking at M2 being the moisture content that's just under the surface of the fuel, we look at M2 being the moisture content from the previous time step. So that one simplification allows us to make the assumption that basically the current conditions drive a rate of change of moisture of the fuel, and then the fuel is small enough that it equilibrates to those changes before the next time step. But it means that all these things we can simplify down from 880 calculations per hour to 1 calculation per hour. And that 1 calculation can then be used to derive tables. So with the diffusivity, we found that we could simplify it because the way that Nelson had it set up, it was a function of several other variables, but one of them being relative humidity, and we did a sensitivity analysis of the diffusivity equations, and it turns out it doesn't matter that much, which means that we can simplify diffusivity in this thing, which is kind of the fundamental underpinnings of all of the physics of how the model works, down to just estimating the surface temperature and a moisture fraction, which we derive as the moisture fraction from the previous time step. So the new model that we have runs on the hourly field measurements of temp and relative humidity, and it does require estimates of rainfall and solar radiation, but it's not going to be super sensitive to to small errors in those things. So they can be estimated, or at the end I'll show you an example where you can grab them in real time as inputs. So the model calculations basically consist of 3 states, and only one state applies at any given time. It's either raining, it's either in an evaporation state where the moisture content is above 30%, meaning that the fuel itself is saturated and the only moisture flow is coming from the surface to the atmosphere, or vice versa. Or it's in the diffusion state, which is when the moisture content is below 30%, which is considered fiber saturation for the fuel. So the entire model just works on three corrections, or 3 modifiers to a previous moisture content measurement or estimate. The very first one is whether or not it rained over the last observational period. If it rained over the last observation period, all you have to do is estimate a rainfall correction and skip everything else. And if it didn't rain, you just have to determine if it was above fiber saturation or below, which tells you if we're estimating evaporation or if we're estimating the actual moisture correction. And then there's a well-established body of literature that shows that fuels don't wet up and dry down at the same rate. And that's kind of built into the Nelson model logic. It's called hysteresis. So this simple set of tables actually deals with hysteresis by determining whether or not, once you're below 30%, it determines whether or not your previous moisture is actually above or below the current equilibrium moisture. And depending on that, you use a different set of tables. So this is a graphical depiction of what it looks like. Basically, you start out with a previous fine fuel moisture. If you're doing these measurements in the field over time, then you would just carry over, after you made a calculation, you carry over the fine dead fuel moisture from the previous observation to start the calculation for the current observation. If you don't have that, you just estimate it based on the equilibrium moisture content, which we'll show you an example of how that works. It's pretty straightforward. But basically, once you figure out what state you're in, whether or not it's raining, whether or not you're above or below fiber saturation, you determine one of these 3 correction factors. Only one of these 3 factors actually applies at any given time step. So if it hasn't rained and the fuels are below 30% moisture content, then you're always using a moisture correction factor. If it hasn't rained and the fuels are above 30%, then you use an evaporation correction factor. And these are quite simple, so you'll see. Hopefully, don't let it intimidate you initially, because I think you'll see that it's not too bad. This diagram kind of explains the logic or steps of what actually goes into what, and I'll identify each one of these tables separately later. So essentially, the air temperature and the solar radiation, so the air temperature that you measure and the solar radiation that you estimate in a couple of methods that I'll show you in a minute, actually feed into a fuel surface temperature calculation, which is used throughout the rest of the table calculations, and that fuel surface temperature, along with relative humidity, is used to calculate the equilibrium moisture content. And we'll do a more clear example, but I just want to illustrate that there's basically, you're estimating 3 correction factors. They have slightly different inputs, but they're all on the data sheet for field collection to make it relatively straightforward to calculate. So the first thing is, after you make your weather observations of temperature and humidity, we estimate solar radiation. So solar radiation isn't a super sensitive input, so we can use some rules of thumb if it doesn't exist, or we can actually generate plots like this, which actually allow us to go in for a given month and day. We can actually see, or a given month and hour of the day, we can see what the maximum solar radiation is for a particular place. But there's a website that's even faster and easier that we'll show you at the end to estimate solar radiation. So once you measure your air temperature, estimate solar radiation, you go to table 1 and you look up the fuel surface temperature. So in this case, if the air temperature was 90 degrees and we were at kind of a midday solar radiation at 800 watts per meter squared, our fuel surface temperature is 117 degrees Fahrenheit. This table is built off of the energy balance that's in Nelson, so the numbers are actually identical, even though it's a quite simple. For cloud cover or canopy, we can just use a simple 50-50 rule. So if you have canopy cover or cloud cover that's greater than 50%, we can reduce the solar radiation by half or multiply it by 50% as a rule of thumb. The second thing we do is after we've estimated that surface temperature, you estimate the equilibrium moisture content and record it on the data sheet. So the equilibrium moisture content is just calculated from the fuel surface temperature and the relative humidity. So in this case, if the fuel surface temperature, like we just estimated, was rounded down to 115 and the relative humidity was 65%, then we can see that our equilibrium moisture content is 10%. And we can record that on our data sheet. Depending on what state you're in, you estimate one of 3 correction factors. So if we were trying to estimate rainfall as a correction factor and it rained 1/10 of an inch, we can come here. It's a little small, but we can see that our correction factor is 30%, meaning that we can essentially, so we'll record that on our data sheet, and we'll have a worked example at the end to try to bring all this together. If it's not raining, but the fuels are above fiber saturation, so above 30%, then we use the surface temperature that we estimated to calculate an evaporation factor. Basically, it's equivalent to the moisture percentage that's evaporated under each surface temperature regime. So in this case, if our surface temperature was 90 degrees, we would record -6 on our data sheet, because that's telling us that we basically evaporated 6% of the moisture away from that fuel. If it hasn't rained and the moisture content is below fiber saturation, then we just use the last set of tables. So tables 5 or 6. They're based on the previous moisture content of that's recorded on your data sheet and whether or not you're adsorbing or desorbing fuel moisture. And that's just determined from whether or not the previous moisture content is greater than or less than the equilibrium moisture content that you just calculated. So if you think about what that means, if your previous moisture content is higher than the current equilibrium moisture content, it means that fuel is very likely to be losing moisture or desorbing moisture. If the opposite is true, it would mean that fuel would be essentially absorbing moisture from the atmosphere. So there's basically just 2 sets of reference tables. There's one reference table for desorbing or losing moisture, one for adsorbing or gaining it. The way the tables look, you basically identify your current the fuel surface temperature that's already been recorded on the data sheet. We know that ours was 117% from our example, but these are pretty low moisture content regimes, so they're probably pretty close to their equilibrium moisture. But if we were here in a relatively low temperature, so say 69 degrees, and a relative humidity in 65%, then we would record 3 on the data sheet. So all of these things basically mean that we can generate a set of tables for field use that are also a set of equations that can be integrated into mobile applications or into into fire behavior applications like Behave Plus or Farsight. So if we look at how this thing performs, we don't expect it to be perfect, but this is a full year of data, so 8,755 hourly weather observations. Fuel moisture is calculated using the full Nelson logic, the fully physically based model, and our simplified model that basically is just one calculation per time step. There's quite a bit of scatter, and the R-squareds are reasonably high actually, but if we look at, it's more informative to look at how the day-to-day variations go. So this is actually a comparison of the new model in red to the Nelson model in blue for a few weeks of data. And what you see is it's really capturing these diurnal variations in fuel moisture. It's capturing the rainfall events, and it's also going above 40% frequently. And as Jim said earlier, the moisture of extinction of all the fuel models that are used in the South is 40%. So if the fuel moisture calculations never get that high, it's going to say that fires always spread. But this new method actually does accomplish this goal of trying to have something that's more dynamic, that incorporates the rainfall, it incorporates the weather, and all these things that are important. So I showed you the long, hard way, and now I'm going to show you the easy way. What we did is we developed since it's based on actual applications or an actual equation, we can program it and build it into tools. So this, if this web address, the www.wifis.net/ffmc, will take you to this little calculator, and we'll do a live example of it here just to show you what that looks like. So when you open up that page, it comes up with a set of default starting values. You can go in and set your current measurement for temperature and relative humidity, and let's say it's 90 and 45%. But since this is your very first observation, you don't have a previous moisture content. As I said, it's important to have that ahead of time. All you have to do is highlight this field and double click in it, and it'll estimate a starting moisture content for you from the equilibrium moisture content. You can set your solar radiation with a slider, and you can actually add some precip to see what the effects are. So this is a mobile enabled application, so it'll work on a phone. You can double tap instead of double click. You can slide things around, but it really exposes these calculations in a way that's very that really simplifies this process. So rather than using the tables, you can use these, but you can copy that. So for your next observation, you can copy to previous. So when we do our second set of observations an hour later, we just copy to previous our starting moisture content, and then we change our temperature, humidity measurements, and see what happens. So we can see the change in the moisture content here as a function of our next observation. So it's a pretty straightforward thing that actually exposes all the functionality, and yet still basically is 100% consistent with the way the tables are formed. So if we go back to the presentation, so that the previous application is mobile based, which means you have to have either a Wi-Fi or a mobile data connection to make it work. But we're working with the University of Montana with Jim Rittering, and they have a really great mobile app for fire weather calculations in the field, and our intention is to basically build these calculations directly into this mobile application, and then also to build in a solar radiation calculator so you don't have to worry about that input, to really kind of tighten up how we deliver this. The tables themselves they can be used, and they do work just fine, but I think that these mobile apps, the one I showed you before, and then as we move into this iOS and Android app, are going to be even more useful. So if we move forward, we'll just look at a worked example. So in the PDF, one of the things I didn't show you is when you go to that website, the www.wifis.net, you can actually also go to, if you do FFMC/docs, it takes you to a directory that that will give you a packet, and that packet is a PDF packet that has the flowchart for how these calculations are done. It has all of these tables in one PDF, and you basically can just print it double-sided, staple it together, and have a set of the tables that you can use in the field. But if we look at it, has this data sheet in there. It's not filled in like the worked example here, but basically it has data sheets that you can print out and have in the field to kind of help you guide through the calculations with the tables. But in this case, if you just measure your temperature and humidity, this is for St. Mark's in Florida. Basically measure your temperature and humidity and estimate the rainfall from available sources, which I'll show you the one that I use for this example. It works super well after we get done with this work example. Again, you just use table 1 to estimate the surface temperature, use table 2 to estimate the equilibrium moisture content after you have that surface temperature, and then you estimate one of these 3 correction factors. So in this case, this is our first observation, so we carry over our equilibrium moisture content as our previous moisture content. The next time step will show you how that works, basically carrying over the final calculated one to the next hour. But all we have to do is estimate one of these 3 correction factors depending on what the state of the fuel is at the time. So in this case, our previous moisture content is 19%, which is below fiber saturation, which means that we have moisture diffusion inside the fuel. So we use the moisture correction factor, and that we can go to the table and look it up and get our correction. And then all we do is just add the previous moisture content to our 3 correction factors. Only one of them applies, the other 2 are set to 0, and get our moisture content for the current time step. So essentially we carry over our 19 as our equilibrium moisture content to the first observation, and that only applies for the first time. We use that to go to the right table, in this case the adsorption table, and we look up 19% adsorption, look up our temperature, our surface temperature of 90 degrees, and our relative humidity in this case was actually 94. So our correction factor is -1, which means that the moisture is dry, that the fuels are drying out, and then we record our final number as the sum of 19 plus 0 plus 0 plus -1, which is essentially just -1. So 19 minus 1 is 18, and that's our fine dead fuel moisture for the hour. So the next observation, all we do is carry over that 18 down to make that our previous moisture in our data sheet, and then we do the same calculations. And you can see here that we didn't have a lot of variation in humidity, and eventually at 12 p.m. on this day it rained. So our carryover moisture was 14% as the fuels were drying out. It rained. We record our rainfall correction factor and set the other two correction factors to 0 and then add it all up. So essentially you just work your way through this process to get to do the calculations by hand or using paper. So just coming back to this to try to bring this together a little bit. Our weather observations are hourly. They're estimated or measured directly, particularly in the case of temperature and humidity. We know we can use a belt weather kit or Kestrel to measure those. Solar radiation we'll estimate from the next example. All the calculations are based on fuel surface temperature in all of the tables. And the equilibrium moisture content tells us whether or not the fuels are wetting or drying, and help us determine which of the correction factor tables to use. So as I said before, it's not like how we used to do it, but it is a more complete representation of how the fuels actually wet and dry, and it's completely consistent with all of the other modeling logic that's used in every other system that we have around the country. So I'll share an example of where you can actually retrieve the solar radiation data in real time. If you have an internet connection or a Wi-Fi connection, you can just go to ros.dri.edu, which will summarize the weather data for the ROS stations that are available. And a lot of these things aren't that important, but with something like rainfall, you can actually just keep a small rain gauge that can be put out. Granted, we're probably not going to be doing a whole lot of operations if it's raining, so you can look these things up ahead of time to figure out how much it rained, and that gives you an idea of how long it's going to take for things to dry out. But in this case, you go to ros.dri, so the previous address, and we just click on one of these points. We go to a daily summary, and that daily summary helps us. The daily summary helps us, or gives us a summary of the data for a particular day, but it's already going to default to the current day. So this was an example from yesterday that I pulled, and you don't have to do anything except just press this button that says Submit Info. And if you do that, you get a summary of the weather measured at that station. It's also a good sanity check for your own field measured weather, but you can derive two fields from this to help guide your application of the tables themselves. So how much it rained in this far right hand column over here, or the solar radiation. And the only weird thing about this, which I literally had to look it up, is that it reports solar radiation in units of Langleys, which is, I didn't even know what it was. That's how out of it I am, I guess. But it's relatively simple to convert. So you just multiply this number that's in the table, the 28 or 58.2 by 11.63 to give you your solar radiation in watts per meter squared, which is what the Nelson model and our new SimpleFFMC model use. I recognize that this is not the way that it's always been done, and I probably can't do it justice to communicate the actual simplicity of this in a webinar without being face-to-face, but I found this quote that seemed appropriate because it just says the secret of change is to focus all of your energy not on fighting the old, but on building the new. And I really feel like that this particular process that we've built and this set of tables and this preliminary application move us in a new direction for how we actually estimate fine fuel moisture in the field, and how we apply it in other applications that need this information. And that the transition is going to take a little bit of a different kind of thought, but the power is immeasurable of this kind of new logic. So the model itself is simple, could easily calculated on hourly field measured weather data or estimated locally. We still have to test it and evaluate it, but I'm I'm very confident that the same model that we developed in the South with that's calibrated even for southern fuels is going to work everywhere, and it's going to give us something that we've never really had before, which is a way to really characterize the dynamic nature of fuels and how they wet and dry. So I think a lot of this stuff's going to help us improve the way we estimate fuel that's in the Fireline Handbook or the IRPG, and also how we plug it into the applications that need it. So with that, I'll stop and take questions.
All right. Once again, if you joined us during the presentation, my name is David Godwin, and I'm the coordinator for the Southern Fire Exchange. And this was a great presentation by Jim Brenner and Matt Jolly on their new SimpleFFMC fine dead fuel moisture estimation tool. So we had a few questions that came in. We'll go ahead and address those first. If you guys have more questions, please go ahead and start typing them into the chat window in the lower left-hand corner of your screen. Just to clarify, one of the questions that came in from Dave Finn, he says, do you factor wind speed into your calculations at all, or could you talk about that a little bit?
Yeah, so the model actually has a place that wind speed fits in the convective heat transfer, so that it actually does have the physical representation of how it affects the heating and cooling of the fuel, but it's assumed to be constant, and we know that that's wrong. So one of the things that I actually have in the works, or that I'm thinking about for the future, is trying to pull that out and just allow that to be an input, because it's another thing that we can easily measure in the field. We know it affects the drying rates of fuels, but we don't have any way to incorporate it. So the short answer is it's not there right now, but it can be in the future.
Mm-hmm. Was it part of the original Nelson model?
It's not. No, he actually assumed a fixed. Wind speed is in there, but he basically assumed that it was invariant.
Mm-hmm.
So it's like a fixed 0.1 meters per second wind or something. Something not very basically a constant.
Yeah. Another question, kind of following up on that, from Michael Ward, he was asking about the arrangement of the fuel.
So yeah, one of the things that we kind of have to do is treat them as a bulk property when we're modeling the fuel moisture, and we know that the bulk properties are going to affect the diffusion rates of moisture in and out of the fuel. So again, it's one of those things that we can probably improve over time by characterizing the sort of bulk density of fuel and how that affects the moisture transport in that the upper litter horizon that we're really trying to model.
Mm-hmm. And I imagine we kind of following on both of those. Question that came in about edaphic conditions, and it seems like edaphic conditions would confound the correction factors. Any research considering this covariate?
Probably need them to describe a little bit more about what they're asking in terms of edaphic conditions.
It's like he's typing in now. Let him address that.
Yeah, the journal is actually the Canadian Journal of Forest Research. I do see that name there. Mm-hmm. Yeah, so that's what. So the pooled water and saturated soils that are going to be an issue, because what we're doing is modeling from the top down. Mm-hmm. We're not modeling any transport of water from the bottom up. But we do have some research going on at the lab that's actually focusing on the wetting drying dynamics of particularly organics and saturated soils, and how that actually ties back in. So it's just a limitation right now. And yeah, I totally agree about the mobile version and location, and I think that's something we can actually do. I know for sure that we can do that, and probably pull the closest data. One of the things that we haven't tapped into yet is a direct connection to WIMS, which would allow us to pull the most current hour of solar radiation and rainfall, because this same model is actually running in WIMS, but it wouldn't have the absolute local conditions that are measured from the temperature and humidity. But I'm definitely sure that with a really good mobile app, we can use the location and do a much better job of pre-populating that stuff. And that is something that I'm absolutely going to do. I mean, I recognize that it's kind of a stretch to ask people to try to estimate or put in values for solar radiation and precipitation right now. So we're basically we're gonna try to simplify that as much as we can, make it more available.
Automate some of that in the mobile app.
Yeah, definitely. So I think we can just go to wherever the person, use the geolocation on a phone, go to the closest station and pre-populate the last hour's observation.
Could you clarify what you put in for rainfall at time step 1? Is that recorded rainfall over what period?
It'd be recorded rainfall over the last hour. It doesn't take long for it to go up or down. So it's usually everything that's recorded is based on the hour. And I'm pretty certain that we can actually just put in a time since last observation to actually make it go either shorter or longer if you're not making hourly observations. And the ETA for the mobile app, I suspect that this fall we'll have a confab with U of M folks and start getting it plugged into a prototype mode with them. They definitely are on board with it and they're interested in doing it. And I even got contacted by the folks at Kestrel, and there's a possibility that we can actually build this into the actual Kestrel device in the future with some assumptions or to use some ways to estimate the things that we can't measure. The initial moisture content is determined from the equilibrium moisture content that you calculate from table 2. So at your first time step, when you don't have any previous weather observation, you just record the equilibrium moisture content as your previous moisture content and move forward from there. And then the next time you make a weather observation, you just carry over the previous one into that column.
All right. Well, it looks like we've come up to the end of our hour. See if there's any last question that comes in. So
and again, if you're in that mobile app, as soon as you set the temperature, relative humidity, and solar radiation and double-click in the previous moisture content field, it'll automatically calculate the equilibrium moisture content for you and plug it back in. So, yeah. But you only have to do that once.
All right. Well, it looks like we have run up to the end of our time allotment today. I'd like to thank Matt, Jim, and Alan for joining us. We've included links there you can see on your screen and also in the box on the side that says web links. You can click any of those and it will automatically load it up into your browser. And those go to the web app that he demonstrated earlier, the final report that came out of their project, the lookup tables, and a link to a new Southern Fire Exchange fact sheet that provides some information summarizing what you saw today in their presentation. We do ask that those of you who have joined us to please take a couple of minutes to click on that Qualtrics webinar link on the current slide, and you can let us know how we can tailor our future webinars to better suit your fire science needs, and also give some feedback to Jim and Matt. We'll share the results with them, and they can use that as they continue their project. Our webinar today was recorded, and we'll have it archived on YouTube in frames at a later date, and we'll be sending that link out to everyone who registered so you can share it with your colleagues who couldn't join us. And thanks everybody who joined us today, and we hope that this webinar will be useful in your fire management and fire research programs. And happy birthday, Matt, and congratulations on your retirement, Jim. We really appreciate you guys for joining us.